So last time binomial coefficients were introduced, and we saw that binomial coefficients were the components of Pascal's triangle. So here we're used to thinking about Pascal's triangle in terms of integers, where we put ones down the exterior sides, and to get an interior number we add the two that come above it. So 1 plus 1 equals 2, 4 plus 6 equals 10, 3 plus 1 equals 4. But in each case, each one of these components here corresponds to a binomial coefficient. So we have 0, choose 0, 1, choose 0, 1, choose 1, and so on. There are really some very, very beautiful patterns that you can observe in Pascal's triangle, and these lead to identities involving binomial coefficients. So one of the very first things you have probably noticed is that they're very symmetric. There is a line of reflection where everything is the same across the line. So this leads us to look at our binomial coefficients. That would mean that 5 choose 0 has to be the same thing as 5 choose 5 in the reflected version. So in terms of the reflection pattern, what does that mean for our binomial coefficients as an identity? We get that n choose k, wherever you go, the nth row, k components in from the left is going to be the same as n choose k minus 1, so that would be k components in from the right. Another beautiful identity is the way that the triangle is created in and of itself. You will remember that if you take two adjacent entries and you add them, you get the entry between it on the line below. This happens regularly. So that means 4 choose 1 plus 4 choose 2 is going to be 5 choose 2, or 3 choose 2 plus 3 choose 3 is going to be 4 choose 3. And if you try to generalize this to two consecutive binomial coefficients, we get the second identity that says n choose k plus n choose k plus 1 gives us n plus 1 choose k plus 1. So the n plus 1 means we went down a row, the k plus 1 means we kept the larger subset size. One of my favorites is called the hockey stick identity, and if you add the numbers down this diagonal, 1 plus 2 plus 3 plus 4, and then you sort of draw the hockey stick end, you get the answer. That's 10. Here we have 1 plus 3 plus 6 is also 10. Or we can take the outside edge. 1 plus 1 plus 1 plus 1 plus 1 is 5. And as long as you start somewhere on this outside edge and follow the line parallel to the outer edge on the left, wherever you stop, the sum of those binomial coefficients will equal the hockey stick end that you draw. So how do we write that as an identity? Oops. We write that as, so that we would start here on the rightmost edge, so we would start with a k choose k. As we come down the diagonal, notice that the size of the subset remains the same in each case. It's always the same subset size. So if we're doing k choose k, we're looking at k subset sizes here, and when you take the hockey stick angle, you've come down a row, so the n plus 1 m row goes to the m plus first row, and the size of your subset increased by 1. So it went from k to k plus 1. And then finally, the last identity that I'm going to put down here is one that we proved in class previously on the first day by induction. The sum as k goes from 1 to n of k, the sum of the first n positive integers, is n times n plus 1 over 2, but this formula is just the formula for n plus 1 choose 2. So those are the 4 identities, and there are hundreds of identities that can be found, but we're going to look at these 4 and prove them combinatorially. Let's talk about what a combinatorial proof is. It's a proof that uses counting arguments to prove that both sides of an identity are counting the same thing in 2 different ways. There are really 2 fundamental types, and we will stick primarily to the first type, which is to ask a question and just answer it 2 different ways. Because it's the same question, those 2 answers must be the same. A second way is to describe 2 sets and essentially match the elements between the 2 sets up, and then count the exceptions between those sets. That often will lead to an identity as well. So let's look at identity 1, that n choose k is the same as n choose n minus k. Start by asking a question. Take the most direct question you can. Don't try to be overly complicated. We want a question essentially whose answer is n choose k. So the questions I come up with is very direct. How many ways can you create a subset of size k from the set 1 through n? Well, there are n objects. We're selecting k of them. The answer is going to be n choose k. So answer 1 is n choose k. Answer 2 we're going to do differently. This time, instead of choosing the objects to be in the set from the set 1 through n, we're going to choose the objects to throw away from the set. So instead, select n minus k objects to throw away. What remains will be a k set, and there are n choose n minus k ways to select the trash. But you've ended up with a set of size k as a result. Because answer 1 and answer 2 are answers to the same simple question, we conclude that the 2 answers are equal. So n choose k equals n choose n minus k. Now I know you could have proven this almost instantaneously by just using the algebraic definition of binomial coefficient, but I wanted you to see a combinatorial proof in action. Let's do the other 3 directly, and I put it all down. Don't let it scare you. We'll take it a little bit at a time. So this is the sum rule, that if you take 2 adjacent binomial coefficients and add them together, what you get is the binomial coefficient between them, 1 row down. So focus on which side is simpler and ask a question that has that side as its answer. I hope you agree with me that this is the simple side of the identity here, and a question that we could ask is, how many ways can you form a subset of size k plus 1 from the set of elements 1, 2, 3 up to n plus 1? The direct answer is the binomial coefficient n plus 1 choose k plus 1, because we have n plus 1 objects and we're selecting k plus 1 objects for the set. Answer 2 is a little bit more complicated, and it's going to be broken down into 2 cases. Pick your favorite element from the set. My favorite element is the number 1. And break the cases down based on whether 1 is included in the subset or not. If case 1 is included as an element of the set, then we have to pick the remaining elements in the k plus 1 subset. Since there are k elements to be determined, they can only be selected from the elements except for 1. So that's 2, 3, up to n plus 1. Well, this is a total of n elements. So we're selecting k objects from n elements, and this can be accomplished in n choose k ways. That's if 1 is in the set. If 1 is not in the set, then we're selecting the k plus 1 subset entirely from 2, 3, 4, up to n plus 1. So case 2 can be accomplished in n, because that's the size of this set. Choose k plus 1. So to get the answer for number 2, we have to add up the possibilities for case 1 and case 2, and we end up with n choose k plus n choose k plus 1. Equating answer 1 to answer 2 gives us the identity we were looking for. Identity 3 was the hockey stick identity. Again, start with as simple a question as you can begin that answers this side of the identity, this simple side of the identity, and exactly the same question as we asked in our previous identity works. How many ways can you form a subset of size k plus 1 from the set 1, 2, 3 up to n plus 1? The direct answer, as it was before, is n plus 1 choose k plus 1. And answer 2 is going to be breaking all of the subsets down based on the largest element in the subset. So if the largest element is called m plus 1, and that largest element is in our subset of size k plus 1, then the remaining elements that we are allowed to pick for our subset, there will be k of them, have to be smaller than m plus 1. So they come from the set 1, 2, up to m. So we're picking k elements from a set with n elements, and this can be done in m choose k ways. Now, we have to worry about what the biggest element can be. So if my subset has size k plus 1, my largest elements, well, it could be as small as k plus 1 itself. That's if the subset was 1, 2, 3, 4, up to k plus 1. And it can increase all the way up to the maximum element of the set, n plus 1. So these are the different cases where the largest element is k plus 1, where the largest element is k plus 2, where the largest element is n plus 1. So our largest element, which we're calling m plus 1, has to be between k plus 1 and n plus 1. Well, that means the cases m really range between k and n. So to add up all the cases here, we're going to have a sum as m goes between k and n of m choose k. And that is exactly, when you equate answer 1 and answer 2, the identity in summation form. Our last identity is going to add up the first n positive integers. We proved this before using induction. We showed that it equals n times n plus 1 over 2. And remember, this is just the binomial coefficient n plus 1 choose 2. Do you see that this is actually a special case of identity 3? We could just say, this is a special case of identity 3 and be done. Make sure you can answer that. Perhaps as we go through the direct proof, you will see exactly what I mean. So we want a question whose answer is n plus 1 choose 2, and that question can be, in how many ways can you form a subset of size 2 from the set of 1 through n? The first answer is the direct one, that we are selecting 2 elements from n, so there are n choose 2 ways to do it. The second answer worries about the largest element in the subset. So if the largest element in my 2-element subset is k plus 1, then I have to pick the remaining element from the set 1 through k. This can be done in k choose 1 ways, and k choose 1 is just k. So the largest element is going to range between 2 and n plus 1, which means k itself is going to range between 1 and n. So answer 2 is the sum over all those cases as k goes from 1 to n of k. Equating answer 1 and answer 2, we get the conclusion that n plus 1 choose 2 is the sum as k goes from 1 to n of k. You'll have some combinatorial proofs to play with, and if you think about it as counting, it might not seem like a proof.